Here we have a pre-calculus problem. Okay, let's go to the question. Which one choice below A, B, C, D, and E accurately describes the behavior of the function f of x equals to x square 94 over absolute value of x 92 at x equals to 2. So the first option says, option A says f is continuous at x equals to 2. And the second one says f has a removable discontinuity at x equals to 2. The third one is about infinite discontinuity at x equals to 2. The fourth one is about jump discontinuity at x equals to 2. The last one is both infinite discontinuity and a removable discontinuity at x equals to 2. So it's really an excellent question in pre-calculus because this question is talking about all types of discontinuities and also continuity at a particular value of x. Okay, now let me consider the first option, that is f is continuous at x equals to 2. So whenever I want to check whether a function is continuous at a particular value of x, so it has to satisfy three conditions. What are the three conditions? So the first condition is, so we have to plug in the given value for x into the function. So that is when I plug in the given value of x, that is when I plug in x equals to 2 into the function over here, I'll be getting f of 2. So when I evaluate the value of f of 2, it has to be a real value. This is the first condition. Okay, when the first condition is met, we have to go to the second condition. That is, I have to evaluate limit of the function at the given value of x. That is, I have to evaluate limit at x equals to 2. So limit x tends to 2 f of x. I have to evaluate this limit, and I must be getting a real value as a result for this limit. Okay, now the third condition. So the third condition, what I need to do is I have to check the results of the step 1 value, step 2 value. So both the step 1 value and step 2 value must be equal. That's the third condition. That is, limit x tends to 2 f of x must be equal to f of 2. So this is the result of step 2. This is the result of step 1. So both these values must be equal. So that's the third condition. Okay, if all these three conditions are satisfied, then I can say that the given function f is continuous at x equals to 2. Okay, so for that, first we have to verify the first condition. That is, I have to find the value of f of 2. It has to be defined. That is, we must be getting a real value as a result for f of 2. So for that, I have to plug in x equals to 2 into the function over here. So the given function is f of x equals to x square negative 4 over absolute value of x 92. Now what I need to do is I have to plug in x equals to 2. So then when I do so, I'm getting 2 square negative 4 over absolute value of 2 negative 2. So 2 square is 4 negative 4 over, so here 2 negative 2 is 0. Absolute value of 0 is still 0. So if I simplify the numerator, I'm getting 0, 0 over 0. Okay, so here, so we have to consider the denominator. The denominator is 0. In a fraction, if the denominator is 0, then the fraction, the value of the fraction is considered as undefined. Let me write it. And when I look at this 0 over 0, so many people will decide it's an indeterminate form. How can we say it's undefined? So when I get this result 0 over 0, when evaluate a particular limit, it's called indeterminate form. But I don't get 0 over 0 when I evaluate a limit. I get this result 0 over 0 when I evaluate the function at a particular value of the variable, that is x equals to 2. So in evaluation of a function, if we get 0 over 0, it's not indeterminate form, it is undefined. So f of 2, when I evaluate f of 2, I don't get real value. It becomes undefined. So when I check the one for the first of the three conditions explained over here, even the first condition itself is not satisfied. Since the first condition itself is not satisfied, I don't have to proceed with the remaining two conditions. So the function is not continuous at x equals to 2 because the result of f of 2 is not a real value. The f of 2 becomes undefined. So the first option A is incorrect. That is, f is continuous at x equals to 2 is incorrect because f is discontinuous or f is not continuous at x equals to 2. Okay, now we can go to option B. Let me erase the stuff I have discussed over here. Okay, now we can discuss option B, that is f as a removable discontinuity at x equals to 2. Already we know that f of 2 equals to undefined. In this situation, that is when f of 2 is undefined, and if I want to check f as a removable discontinuity at x equals to 2, what I need to do is I have to find the left side limit and right side limit of f of x. That is, limit x tends to 2 minus. 2 minus means there is a negative sign on the right side top corner of this 2. It indicates as left side limit of 2, and also I have to find the right side limit of 2, that is limit x tends to 2 positive. So this positive sign over here indicates right side limit of 2 f of x. So the left side limit of x tends to 2, the right side limit of x tends to 2 for the given function f of x, must be equal. So when f of 2 is undefined and also the left side limit of 2 and right side limit of 2 for the function f of x are equal, then we can say f of s as a removable discontinuity at x is equal to 2. Okay, so how do you have to evaluate the left side limit and right side limit for f of x? So just consider the given function over here. It contains an absolute part in denominator. So whenever a function contains an absolute part like x negative or something like that inside the absolute value, it can be redefined. I mean, the given function can be redefined as a piecewise function. So once we redefine the given function as a piecewise function, we can find the left side limit and right side limit of 2, and we can check whether and also both of them must be real numbers. That's very important. The left side limit of the left side limit of 2 for f of x and the right side limit of 2 for f of x, both of them must be real numbers and both of them must be equal. And also more important, so the initial condition is f of 2 is undefined. So in this situation, we find the left side limit of 2 and the right side limit of 2 for the function f of x when f of 2 is undefined. So when both of them are real numbers and they are equal, we can say that f has a removable discontinuity at x equals to 2. Okay, so now what we need to do is first we have to redefine the given function as a piecewise function. How do we have to do that? So for that, let's consider only the absolute part we have in denominator, that is absolute value of x negative 2. Okay, now let me consider the stuff we have inside the absolute value, that is x negative 2. So this is the expression we have inside the absolute sign. Okay, so here for what value of x, this x negative 2 will become 0. Here we don't have absolute sign, I just have parenthesis for x negative 2. For what value of x, this expression will become 0. So it's very simple. When I plug in x equals to 2, 2 negative 2, this will become 0. Now just mark that number, the value of x which makes this expression 0 on the real number line, that is 2. So x equals to 2 makes this expression 0. Now if I consider the values on the left side of 2, for example, on the left side of 2 we have 1, 0, negative 1. If I consider the values on the left side of 2, so what is the sign of this expression? For example, if I plug in x equals to 1, which is on the left side of 2, so it will become negative or positive. So when I plug in x equals to 1, 1 negative 2, it will become negative. If I plug in x equals to 0, 0 negative 2, it will become negative. If I plug in negative 1 for x, negative 1 negative 2, again it will become negative 3. So if I consider the values on the left side of 2, the expression over here becomes negative. So then this absolute part will be redefined as negative of x minus 2 when x takes the values less than 2, that is when x is less than 2. And also now let me consider the values on the right side of 2, that is 3, 4, 5. So if I consider the values on the right side of 2 for x over here, so what is the sign of this expression x negative 2? It will be positive, because when I plug in x equals to 3, 3 negative 2 will become positive 1. If I plug in x equals to 4, 4 negative 2 will be 2. That's also positive. So this expression will become positive. So since it becomes positive, we can write this expression as it is when x is greater than 2. And also we cannot consider x equals to 2, because at x equals to 2, the function becomes undefined. Already we have discussed this. So I just redefine only this absolute value of x negative 2 as a piecewise function. So when x takes a value less than 2, so the expression we have inside the absolute value becomes negative. So that's why I have taken negative sign for the expression we have inside the absolute value. Okay, now let me redefine the given function as a piecewise function, that is f of x equals to so the first thing is x square negative 4 over, so instead of absolute value of x negative 2, I'm going to take negative of x minus 2. So that means usually absolute value of x negative 2 becomes negative of x minus 2 when x is less than 2. So we can write if x is less than 2. And the second part is x square negative 4 over, if x is greater than 2, then so absolute value of x minus 2 is redefined as just x minus 2. We can write that x minus 2 over here. So what if x is equal to 0? If x is equal to 0, the function becomes undefined. We can write that over here. So now I have redefined the given function as a piecewise function as we have done over here. Okay, now so this is a function, this is a given function. So here we have absolute part in the given function, but so we have redefined this one as a piecewise function. So only if I redefine this one as a piecewise function, I can find the left side limit and right side limit of 2, so that I can check whether the function has a removable discontinuity at x equals to 2. Okay, now let me erase the stuff over here. Just a moment, 1 second. Okay, I erased everything. Okay, now I'm going to find the left side limit and right side limit of 2. So first, let me take the left side limit of 2. That is limit x tends to negative f of x. That means 2, and there is a negative sign over here on the right side top corner. That means x approaches 2 from its left side. So when x approaches 2 from its left side, all the values over here will be less than 2. So when x is less than 2, what piece of x we have to consider? Because we have 3 pieces. What piece do we have to consider for f of x? So when x is less than 2, this is a piece we have to consider for f of x. Oh, let me write over here, limit x tends to 2 negative x square negative 4 over negative of x negative 2. Okay, here we have this function in limit. So whenever we have a function in limit, it can be simplified. But when I consider the function as it is, I cannot simplify. But when we have the same function with limit, it can be simplified. So for that, I have to factor the expression we have in numerator, that is x square negative 4. So x square negative 4 can be written as x square negative 2 square. That is, this 4 can be written as 2 square. Now, this is in the form of a square negative b square. So in algebra, there is an important identity for a square negative b square. That is, actually, this is the difference of 2 squares. Whenever we have a difference of 2 squares in the form a square negative b square, it can be written in the factor form, that is a positive b times a negative b. So this x square negative 2 square is exactly in the form a square negative b square. So this x square negative 2 square, that is the difference of these 2 squares, can be written in factor form. That is x positive 2 times x negative 2. Okay, now so we got the expression x square negative 4 in the form x positive 2 times x negative 2. So now limit extends to 2 negative. So instead of this expression x square negative 4, we can write the factored form, that is x positive 2 times x negative 2 over negative of x negative 2. So this x negative 2 will cancel out. Then I'm getting limit extends to 2 negative. This negative sign can be taken along with the stuff we have over here in numerator, that is x positive 2. Then I'm getting negative of x positive 2. Okay, that's all the simplification I can do with the function we have over here. Now what I need to do is I have to plug in the limit 2 for x over here. And also you may have a doubt. So what do we have to do with the negative sign we have on the right side top corner of 2? This negative sign has nothing to do with the calculation part that we are going to do further. So because this negative sign indicates, so from which side of 2 x approaches. Actually x approaches to, say x approaches to from which side, whether x approaches to from the left side or right side. So this negative sign indicates x approaches to from its left side. That's all. Otherwise this negative sign will not involve in the calculation part, that is in the evaluation of limit. Simply we have to plug in 2 for x over here. So when I do so, I'm getting negative of 2 positive 2. Then I'm getting negative 2 positive 2 will become 4. I just evaluated the left side limit of 2 for the given function f of x, that is equal to negative 4. Okay, now what I need to do is I have to evaluate the right side limit of 2. So let me do it over here. That is limit extends to 2 positive. So this time I write positive sign on the right side top corner of 2. So because x, this time x approaches 2 from its right side. Okay, so let me write f of x over here. Again, let me write the same stuff, that is limit extends to 2 positive. Now, among the 3 pieces of f of x, which piece I have to consider for f of x over here? This time, there is a positive sign over here, that is x approaches 2 from its right side. So when x approaches 2 from its right side, all the values over here will be greater than 2. So that is, we have to consider the piece of f of x where x is greater than 2. So this is the piece of f of x we have to consider. Because for this piece only we have x greater than 2. So for this f of x, I have to plug in this expression, that is x square negative 4 over x negative 2. Okay, now limit extends to 2 positive. Okay, now already we got the factor form of this x square negative 4, that is x positive 2 times x negative 2. Okay, this in denominator we have x negative 2. So this one will cancel out. I'm getting limit extends to 2 positive x positive 2. So already I said this positive sign will not involve in the calculation part because it indicates the side, I mean from which side of 2 x approaches to. So that's it. So x approaches to from its right side. So only that that indication is given by this positive sign. Otherwise it does not involve in the calculation part. So now what I need to do is I have to plug in this 2 for x over here. So when I do so, I'm getting 2 positive 2. So 2 positive 2 becomes 4. Now I got the left side limit of 2, which is negative 4, and also I got the right side limit of 2, that is positive 4. So the left side limit of 2 and the right side limit of 2 for the given function are not equal. Moreover, f of x, f of 2, already we know that f of 2 is undefined. So it's very important condition. When f of t is undefined, in case if I get the same real value for the right side limit of 2 and left side limit of 2, I can say that f the given function has a removable discontinuity at x equals to 2. But f of 2 is undefined. In that situation, I just evaluated the left side limit of 2 and right side limit of 2 for the given function. So even though I get a real number for the left side limit of 2 and the right side limit of 2, they are not equal. So the function f does not have a removable discontinuity at x equals to 2. So the second option, option B, is also incorrect. Okay, now we can move to option C. Okay, let me erase the stuff we have over here. Okay, now let's go to option C. Option C says f as an infinite discontinuity at x equals to 2. So how do you have to verify whether a function has infinite discontinuity at a particular value of x? So for that, we have to evaluate the ordinary limit of 2 for x, that is limit x tends to 2. It can also be called as the double-sided limit of f of x. So the result of this limit has to be either positive infinity or negative infinity. So when I evaluate ordinary limit or double-sided limit for the given function at x equals to 2, if it results positive infinity or negative infinity, then I can say that f as a given function has an infinite discontinuity at x equals to 2. And please notice that I am saying ordinary limit or double-sided limit because I don't mention positive or negative sign on the right side top corner of 2. So it's a double-sided limit. So when I evaluate double-sided limit for x equals to 2 for the function f of x, the result must be either positive infinity or negative infinity. That is, when x approaches 2 for the given function f of x, then the value of f of x must approach either positive infinity or negative infinity, that is unbounded. Then we can say the given function has infinite discontinuity at x equals to 2. Okay, how do we have to do that? So already we have we got the left side limit and right side limit for f of x at x equals to 2. That is, let me write the result. Already we got over. So that is limit x tends to 2 negative f of x. That is, this is left side limit of 2 for x. Already we got this result, that is negative 4, and limit x tends to 2 positive. So this is the right side limit of 2 for x. So equals to positive 4. So the left side limit of 2 and the right side limit of 2, are they equal? No, they are not equal, because here, even though we get real value for left side limit and right side limit of 2, so they are not equal. So whenever the left side limit and right side limit at x equals to 2 are not equal, then we have to say that the ordinary limit or double-sided limit, that is x tends to 2, f of x does not exist. That means when x approaches 2, the value of f of x does not exist. So according to the condition for infinite discontinuity at a particular value of x, so when you take ordinary limit for ordinary limit of x, that is x tends to 2, the value of the function has to approach positive infinity or negative infinity. But when x approaches 2, the value of the function f of x does not exist. The reason is the left side limit and right side limit are not equal. In case, what if the left side limit and right side limit are equal? For example, instead of negative 4, if I have 4, what should I say? Then the ordinary limit must be equal to 4. Whatever real value I'm getting for the left side limit and right side limit, that can be taken as a value for, as a result for ordinary limit. Okay, so but here the left side limit and right side limit are of 2 for x are not equal. So limit x tends to f of x, that is the ordinary limit, does not exist. So the limit x tends to f of x does not approach positive infinity or negative infinity. So option C is also incorrect. That is, f does not, the given function does not have infinite discontinuity at x equals to 2. And already we have seen that is f of 2 equals to undefined. Okay, let me write it. So when f of 2 equals to undefined and the left side limit of 2 and the right side limit of 2 are not equal, so the function does not have removable discontinuity at x equals to 2. That's what we have discussed in option B. Even though we get real values for the left side limit of 2 and right side limit of 2, since they are not equal and also f of 2 is undefined, so we have to decide the function does not have removable discontinuity at x equals to 2. So whenever f of 2 is undefined and at x equals to 2 and the left side limit and right side limit at x equals to 2 are not equal and both of them are real values, so we have to decide the function as jump discontinuity at x equals to 2. How? So let's see with the graph. Okay, so here we have 1, here we have 2, and here we have let's say this is 4, and here we have negative 4. This is x-axis and this is y-axis. And instead of f of x, we can consider a y-axis, a y value over here. So because in any function we have f of x, instead of f of x, we can consider y. Okay, now when x approaches 2 from its left side, f of x approaches, that is y approaches -4. So something like this. So when x approaches 2 from its left side, the y approaches -4, and I use empty circle because at x equals to 2, the function is not defined. And also when x approaches 2 from its right side, f of x approaches 4, that is y approaches +4, something like this. And again, I have to use an empty circle over here because f of 2 is undefined. So like when x approaches 2 from its left side, y approaches, that is f of x approaches -4. When x approaches 2 from its right side, y approaches -4. So y value jumps from -4 to +4. So that's why I'm saying that f has a jump discontinuity at x equals to 2. So then option D is correct. And also, what about option E? Option E says f has both an infinite discontinuity and removable discontinuity at x equals to 2. So that's not true because f does not have removable discontinuity, and also f does not have infinite discontinuity. So that we have discussed in option B and C. So option E also incorrect. The correct answer choice for this question is option D.